Alright, Rolle's theorem. Rolle's theorem is pretty much just like the MVT, mean value theorem. It's just kind of a corollary of it, and it's basically saying that in order for it to work, you just have to make sure that your two endpoints are actually equal each other, okay, so that they're just flat. So that somewhere along the way, no matter how you traveled there, as long as it is continuous and differentiable, just like MVT, then somewhere along the line the slope had to be 0. Okay, you had to, because the average here is actually 0, so it just means then the average, just like the MVT is just an average. Okay, just the MVT can look like that. Okay, so somewhere along the way, as this guy went to here, okay, you had to have the same slope somewhere. Okay, and for instance, it would be right there and right there, so it happened twice. Here, it'll happen here, and then there, and pretty much right there. Okay, so anyways, all you got to do is make sure that these endpoints are actually equal to each other. So f of 0 is going to give us 11. And we just have to verify that f of 4 is going to give us 11 as well. And we got 12 minus, what do I feel like that's, squared. Here we go, 16 times 3, 48, 48 minus 48 is 0. So there we go, 0 plus 11 is just 11. Okay, so Rolle's theorem applies. Rolle's theorem applies, and just make sure we might want to include a statement that says it is differentiable and continuous because it's a quadratic polynomial. All right, so now all you got to do is just find that because these guys equal each other, that means that we have to say that the average rate of change is 0. So 0 has to equal this derivative. Let's find the derivative. 6x minus 12, okay, equals 0. So it looks like, oh, that's an easy one. X equals 2. Now, normally, we want to say that this is C, okay? Okay, so we'll say C equals 2. So at x equals 2, the derivative is 0. Okay, or you can just say that you could just say, yeah, C equals 2 satisfies the theorem. Okay. All right. So let's do the same thing here. So let's go g of 0 equals -7. G of 3 equals not 18 minus 7. Okay, that's 11. So Rolle's does not apply. Because g of 0 does not equal g of 3. Okay, they have to equal each other in order for this to work. All right, the next problem looks like we're minimizing. So this is our optimization problem. We're dealing with a cylindrical can. It holds a liter, which is 1,000 cubic centimeters of liquid. How should the height and radius be chosen to minimize the amount of material needed to manufacture the can? So we are minimizing the amount of material. So the amount of material is actually the surface area. Okay, like you were just cutting the sheet of aluminum or tin, whatever it is. So the surface area of this guy equals, you can draw a picture here. It's a can. Okay, the surface area is going to be the, if you were to cut this guy down the middle, he would basically be, his length would be 2 pi r, Okay, 2 pi r, and then you would have to add, times the height, then you would have to add the area of the two circles. Okay, you'd have to add the area of the two circles. So here's the pi r squared, but you've got two of them that you have to have material for. Okay, that's where this guy comes in. So 2 pi r, that is the area of one of them, but because you got two of them, that's the surface area of both the top and the bottom. And this guy is if this guy was kind of like stretched out, okay, that this width of the sheet is actually the circumference of the circle. So that's why we have this, but then you have to multiply by how high that unraveled sheet is. Okay, so I'm just letting you know where the formula came from. It's not just magical, okay? It's basically kind of cutting the can apart and relating it to its circular structure. So anyways, we're going to recopy this guy over here, even though we wrote it over there. Okay, and we want to maximize this guy, so that is what we will be taking the derivative of. It's got two variables, so what we're going to do is we're going to use this information to get rid of one of the variables, and it's going to be the height. It's just better that way. So we're going to now do the volume of this guy, because that's our given information. The volume of this guy is going to be the area of the circle multiplied by the height. Okay, so we know that the volume is actually 1,000. So what I'm about to do is substitute for h. I think we've done one or two of these types of problems. That's 1,000 equals this. So let's go ahead and solve for h. We're going to put this pi r squared. So these guys cancel out. So now what we've got is you've got the surface area equaling 2 pi r times 1,000 over pi r squared plus 2 pi r squared. So notice that we are h-free. Okay, we are completely h-free. We have used the restriction or the constraint equation, is what this is sometimes called, to allow us to develop a relationship between these variables. That way one of them can be substituted for the single variable calculus that we need to perform. This is kind of convenient because that will cancel out. That will cancel out. You'll have 1r left. So you've got 2,000 over r plus 2 pi r squared. Okay. All right, now this is the guy that we're going to take the derivative of. So here we go. Now we have it as a function of r now, so we're going to write it like this. Okay. What you don't want to do that, because these are two separate words, and just putting the prime there is not enough. You could do this like that. That would be okay. But the prime is usually reserved for function notation. So go ahead. Putting it like this is better. It's the best thing to do. All right, so the derivative of this would be negative 2,000, but then it's going to go to r squared for his derivative, and then this guy would be 4 pi r. Okay. All right, now maxes and mins always happen when the derivative is 0, so let's go ahead and set it to 0. And by setting it to 0, this guy's 0, this guy will swing over to the other side and become positive, so we're going to rewrite that. And for time, I'm just going to go ahead and write it like this. Okay, so now it looks like I'm going to put this r squared over there, and that'll give me, and then the 4 pi will go down below. Okay, r cubed. All right, so 4 will go into 2,000. That's going to be 500 times, so 500 pi equals r, and I'm going to take the cubed root. All right, calculator time. All right. Cubed root, cube root. Cube root is in the math button. So math button number 4, cubed root, and we're going to do 500 divided by pi. 5.42. Just go 5.42. So we'll put approximately 5.42. Excuse me. Oh man, for a second I thought I was not recording. That would have been tragic. So over here with 5.42, I got the radius. Are we sure it's going to be a min and not a max? Well, a max wouldn't make any sense, right? It really wouldn't. But I know on the AP exam, we would have to kind of consider that that we're kind of proving that it is actual minimum, okay? So at 5.4, what does happen to our derivative here? Let's go to the left of it. Let's say 6. Let's plug in 6 here. Let's see, what is that going to be? Negative 2,000 divided by negative 6 squared, 36, plus 4 pi. I know you could probably do this in your head and get some estimates, but I'm just going to make sure. Okay, that is negative. Okay, just want to make sure. All right, so it's decreasing, and then when it should pop back up once I get a value that is higher. Let's go. Wait, did I put 6? I put negative 6. Okay, so that's way over there. Now I'm just going to put positive 6. So let's do that. Okay, so that's still going to be 36. Then that'll be a positive. There we go, positive 19.8. Okay. All right, so that means then that this guy is a minimum. Okay. All right, now there's kind of a little proof there to show that this is a minimum amount of material. And then that tells us then that we can find the height by going ahead and solving for this. We said that the height equals 1,000 divided by pi r, which is 5.42 squared. And this will be approximate, so 1,000 divided by pi times 5.42 squared. Okay, 10.83. So that means that the height, around that, okay. So the dimensions of this guy have to be, the height has to be this, and the radius has to be that. Perfect. It minimizes the surface area, and it keeps the volume at 1,000. Beautiful. All right, we'll stop there, and we'll do the last one in another video.